Today we'll talk about wave equation. I know this also is a repetition for you, but it's always nice to have a nice foundation when we are trying to develop a set of new concepts in this course. So stay with me, enjoy this, just going back in time, that's all. We start with Maxwell's equation. Del cross H equal to sigma plus j omega epsilon times E, and del cross E is minus j omega mu H. We recognize immediately that this is for a source-free region and the medium is lossy because we have sigma. Now, let us take the curl of the first equation, that is del cross H is sigma plus j omega epsilon times del cross E. Now we substitute the value for del cross E from the top second equation and it turns out to be equal to minus j omega mu H, and then we write it in the form as minus gamma square H, where gamma square is given by the tiny equation there. Very important quantity, and we will have to remember this because we will be using it more often. So gamma square is sigma plus j omega epsilon times j omega mu. What is gamma? Gamma is known as the propagation constant. In general, it is a complex quantity. It has a real part alpha, which is known as attenuation constant. Units are Nepper per meter. And it has an imaginary part called beta, which is known as phase constant. Units are radians per meter. Again, this is another one which you are familiar with, but it's good to remember this. Now let's get back to this equation, del cross H. We know the vector identity. This is given by del dot H minus del square H. Now del dot H is 0. That's from Maxwell's equation. Therefore, del square H is equal to gamma square H. Nice result. If you perform the similar kind of operation, instead of starting with Ampere's law del cross H, we start with Faraday's law del cross E is minus j omega mu H, and then take the curl of this equation and then expand it, substitute del dot E equal to 0 because it is source free region. Then we can show that del square E equal to gamma square E. Please do this. This is very important. However trivial it is, please do that. Now, if it is free space, that is sigma is 0, epsilon is epsilon naught, mu is equal to mu naught. In that case, gamma square will become equal to minus omega square mu naught epsilon naught. And we can write that equation, wave equation, as del square E equal to minus beta square E, where beta square is omega square mu naught epsilon naught. This equation del square E equal to gamma square E or del square E equal to minus beta square E, this is known as wave equation because it defines the nature of the wave, the behavior of the electric field in space. Of course, in time we know that it is e to the power of j omega t. We know this result. Now let us take this wave equation and try to expand this in rectangular coordinate system. Now in rectangular coordinate system, the electric field is a function of x, y, z, has three components, one x directed Ex, y directed Ey, and z directed Ez. These are all complex phasors. Now if I substitute this in the wave equation and simply expand, and we take out that Ax, Ay cap, Az cap outside, because Ax, Ay, Az caps, they are not functions of space. Therefore, they are constant and hence they can be taken out of the derivatives, that is taken out of del square operator, and we can component wise make it equal to 0. That is del square Ex minus gamma square Ex equal to 0. Similarly, del square Ey minus gamma square Ey equal to 0, and del square Ez minus gamma square Az equal to 0. Now we can expand del square in terms of rectangular coordinates as del square Ex upon del x square plus del square Ey upon del y square plus del square Ez upon del z square minus gamma square Ax equal to 0. Now we introduce the method of separation of variables. what we assume is Ex, a function of x, y, z, can be written as f of x, a function of x alone, multiplied by g of y, function of y alone, multiplied by h of z, a function of z alone. That is, Ex is a function, a product of three functions which are functions of x, y, and z independently. This is a very big assumption. Next slide I'll tell you what are the conditions under which such an assumption can be made. Now let us substitute this in the top equation. What do we have? Since g and h are not functions of x, they are constants as far as the differentiation with respect to x is concerned. Therefore, they come out of the derivative. Similarly, for y and z components, divide the whole thing by fgh. And what we have is 1 by f d2f by dx square plus 1 by g d2 g by dy square plus 1 by h d2h by dz square equal to gamma square. Since these are all functions of x, y, and z independently, we have removed the partial derivative and made it ordinary derivative. Since each term is a function of x and other term is a function of y, the third term is a function of z, sum of that is equal to a constant. Therefore, each term must be a constant. Otherwise, there is no way we can satisfy this equation. And hence we write 1 by f d2f by dx square equal to gamma x square. Gamma x is a constant. Similarly, 1 by g d2g by dy square is gamma y square, and 1 by h d2h by dz square is gamma z square. And this has to satisfy a condition, that is gamma x square plus gamma y square plus gamma z square must be equal to gamma square. There we go. We still haven't answered the question under what conditions this variable separation of variables method will work. Let's answer this question today or at this point in time. The differential operator must be separable. That means if L is a differential operator, L of f1x f2y upon f1x f2y should be sum of a function of x only plus a function of y only. That's what we saw just now. This operator del square Ex equal to gamma square Ex could be separated into a function of x plus function of y plus function of z. This is first requirement. There are two more requirements. All boundaries must conform to constant coordinate surfaces. In rectangular coordinate system, the boundaries on which the object has certain boundary where we are trying to solve this differential equation, those object boundaries must coincide with x equal to constant, y equal to z constant, and y equal to constant and z equal to constant surfaces. For example, if you are talking about a rectangular waveguide, these rectangular waveguide walls should be parallel to x and y axis or z axis. Only in that case we can apply this kind of a method. Now I am going to introduce a third condition and also a new language. The boundary conditions at x equal to constant or y equal to constant or z equal to constant should be either Dirichlet type. Dirichlet type means the function should go to 0, or Neumann type, that is derivative of the function should go to 0. As we go along, we will come across these two quite often, but currently I am introducing two new words to you. A Dirichlet type boundary condition where the function goes to 0, Neumann type boundary condition where the function prime goes to 0. What is not permitted is on the boundary part of it is Dirichlet and part of it is Neumann is not permitted. So this is something which we should remember. Let us look at the possible solutions of this differential equation d2f upon dx square equal to gamma x square f of x. Gamma x is a complex quantity. Gamma x could be is in general alpha x plus j beta x. Gamma x could be only j beta x, that is when alpha x is equal to 0. then in that case the differential equation will be d2f by dx square equal to minus beta x square fx. If gamma x is only equal to alpha x, then that equation will be straightforward, d2f by dx square equal to alpha x square f of x. Suppose we have a situation where gamma x is equal to j beta x. In that case, the solutions e to the power of minus j beta xx or e to the power of j beta xx will satisfy this differential equation. These are known as traveling waves. Now, this function has zeros when beta xx tends to minus j infinity or beta xx tends to plus j infinity. If you look at the amplitude of this will not change. It remains independent of x. The magnitude of e to the power of minus j beta xx is equal to 1. So it doesn't decay. It keeps propagating to infinity. Now, on the other hand, if you look at the solution cosine beta xx and sine beta xx, this will also satisfy the differential equation. Very straightforward to show that. These are known as standing waves. That means the amplitude of this will go through a 0 minimum and a maximum equal to 1. It varies between 0 and 1. For example, cosine beta x, or let's take sine beta xx will go to 0 when beta xx is equal to plus minus n pi. So it's a periodic function, and this function value will go to 0 periodically. This is a kind of solution we choose when we know that the solution, the final solution, has to satisfy certain boundary condition. That is, if the function has to go to 0 at particular location, then we choose the appropriate value, appropriate form of this solution. Then we have another type of wave called evanescent wave. This is a one which decays very fast as value of x changes. For example, e to the power of minus alpha xx, when alpha xx goes to infinity, the amplitude goes to 0. So as value of x goes from 0 to infinity, the function value decays from 1 towards 0. Similarly, e to the power of alpha xx goes to 0 when alpha xx goes towards minus infinity. That means if you are going towards the minus x direction and you want to have a wave which decays, then you choose this particular functional form e to the power of alpha xx. Similarly, you can also have cosine hyperbolic and sine hyperbolic functions which are also evanescent wave. Now, the attenuating traveling wave is represented by e to the power of minus gamma xx or e to the power of gamma xx, which has a traveling wave component e to the power of minus j beta x, which is multiplied by a quantity and amplitude which decays as a function of x. Therefore, this is an attenuated traveling wave. In real world, our waves will be of this kind, but in our ideal mathematical world, we chose the wave to be pure traveling wave, which is not attenuating. Now, the moment we talk about a wave, we have to think about a velocity associated with wave. So how fast the wave goes? What is the meaning of how fast the wave goes? Let's look at this equation. Suppose we have a solution, a propagating solution, which is f of x equal to e to the power of minus j beta xx. Remember, this is in the phasor form. If you want to plot, you want to physically visualize a wave, then you must bring this into time harmonic form. How do you do that? You multiply it by e to the power of j omega t and take the real part of it, and which turns out to be cosine of omega t minus beta xx. This is a real function. I can plot this function as a function of both space and time. Now, if I were to ask the question, what is omega t minus beta x equal to constant? That is, it is called a constant phase point. Suppose along the x-axis there is a point xp, and we ask the question, we consider the equation omega t minus beta x xp equal to c naught. Now, if you differentiate this function, what we get is omega minus beta x dxp upon dt equal to 0. And dxp by dt tells us how fast this point xp is going with respect to time, or it's moving with respect to time. Xp is a constant phase point, and as a function of time, how fast this constant phase point moves is the phase velocity of that wave. In this case, it is omega by beta. We have another possible solution. What is that? E to the power of plus j beta xx. And what will be the time harmonic representation of this? That will be cosine omega t plus beta xx. And the constant phase point corresponding to that is omega t plus beta x xp, which is equal to c naught. C naught is a constant. Take the derivative, straightforward to show Vp in this case turns out to be omega by beta with a negative sign. That means e to the power of minus j beta xx represents a wave going with positive velocity. It is going in the positive x direction. Whereas e to the power of plus j beta xx represents a wave going in the negative x direction because it has negative phase velocity. Very quick, very interesting way of representing what the wave velocity and the direction of propagation. Of course, there are graphical ways by which you can show exactly the same. Maybe sometime, some other time, I'll show you graphically what is the meaning of all this. We'll probably show you a movie so that you can visualize it better.